Welcome to the Explainer. So today we're taking something that usually sparks a little dread, a grade 12 physics model exam, and we're going to flip it on its head. We're not just grinding through test questions here, we're taking a massive journey of scale. We're going to explore everything from the tangible, everyday forces of pushing boxes up a ramp all the way down to the invisible, chaotic splitting of atoms. And as you'll see, the exact same fundamental laws govern our entire reality.
Okay, let's dive right into this. Here is our roadmap for today. First, conquering the physics exam. Then, mechanics, motion, and forces. After that, fluids, waves, and heat. Next up, electricity and modern physics. And we will wrap it all up with the final equation.
Section 2, Mechanics, which is all about motion and forces. To really start understanding the visible, tangible world of mechanics, we absolutely have to nail down the difference between distance and displacement. Distance is just a measure of the entire total path you traveled, no matter how winding or curved it gets. Displacement, though, that is strictly the shortest straight line from your starting point to your ending point. It's like if you run a massive lap around a track and finish exactly where you started, your distance might be huge, but your displacement is literally zero.
Let's think about how we actually track that kind of motion over time. Imagine a circus clown riding a unicycle in a straight line over a 12-second period. Her velocity is constantly shifting, right? Sometimes she's accelerating, speeding right up to 10 meters per second. Sometimes she's just cruising at a constant speed, and then eventually she hits the brakes and decelerates back down to zero.
So, thinking about that scenario naturally leads to a big question. After those 12 seconds, how far did the clown actually go from her starting point? Well, in physics, we don't guess. The magic trick here is that the total distance traveled is simply the area under the velocity time curve. By just calculating the area of those geometric shapes, the triangles and rectangles, we literally translate pure data into a concrete physical distance. And this brilliantly illustrates what happens when we stop moving in a straight line. Think about a small ball on a string, swinging in a uniform circle on a flat, frictionless table. To stop that ball from just launching across the room in a straight line, that string has to constantly apply an inward force, pulling it right toward the center of the circle. It's such a perfect way to visualize how forces physically bend and shape the path of moving objects. Now, forces aren't just about spinning things in circles, they're about getting actual work done. Take a look at this highly relatable scenario, dragging a heavy 25-kilogram trunk up a 20-degree loading ramp into a truck. Instead of deadlifting that heavy box straight up vertically and completely fighting gravity, you use the ramp. The ramp is basically acting as a simple machine.
So, the crucial takeaway here is the trade-off. Ramps don't magically make the box weigh less. What they do is reduce the force you have to exert. You're trading a longer walk for a much lighter push, making it way easier to beat gravity and the kinetic friction of the ramp itself.
Section 3, Fluids, Waves, and Heat. Let's shift gears from the tangible world of moving heavy boxes to moving heat. Think about a simple pot of water placed on a hot stove. As the water at the bottom heats up, it gets less dense and floats to the top. Then, the cooler, denser water at the top sinks downward to take its place. That creates this continuous, rolling, circulating motion. And that thermodynamic principle right there, that is exactly what defines convection. When that water, or any fluid really, starts moving, the way it flows is super important. The physics exam highlights a stark contrast here. In steady, or laminar flow, the fluid particles just glide perfectly in incredibly smooth parallel layers with almost no mixing. But if you introduce too much speed or a disruption, it breaks down into turbulent flow. That's just total chaos, characterized by irregular motion and strong, messy mixing between all the fluid layers. Moving from flowing liquids to flowing energy, we absolutely have to define waves. The way particles move relative to the direction the wave is actually traveling gives us two main types. First, transverse waves. This is where particles vibrate perpendicular to the wave's path, literally like doing the wave in a sports stadium. Then you have longitudinal waves, like sound moving through the air. Here the particles vibrate parallel to the direction of propagation, compressing and expanding as they travel.
Section 4. Electricity and modern physics.
Okay, leaving the everyday macro world completely behind, just take a second to look at the sheer immense scale of this number. 300 million meters per second. That is the speed of light in a vacuum. It is the ultimate speed limit of our universe and a fundamental constant that governs not just light, but all electromagnetic waves, from radio waves to gamma rays. It literally forms the bedrock of modern physics.
And when we harness those electromagnetic forces, we get to build circuits, like a setup featuring multiple resistors and batteries. When you wire identical resistors in parallel like this, something fascinating happens. Even though the total current splits off into different branches, the potential difference across each resistor stays exactly the same. It's this brilliant little trip of physics that makes our complex electronics actually work.
Speaking of complex electronics, circuits get way smarter than simple resistors. This schematic demystifies how modern computers actually process binary information using logic gates. What we have here is a combination circuit built from a NOR gate on the left feeding directly into a NOT gate on the right.
To really figure out what this circuit is doing, we build a truth table by walking through it step by step. Step 1. Your binary inputs, A and B, enter the NOR gate. Step 2. The NOR gate processes them, outputting a 1 only if both inputs are 0. Step 3. That signal travels right to the NOT gate, which just flips it, turning a 0 to a 1 or a 1 to a 0. By combining these tiny logical flips, physicists and engineers build the insanely complex brains of our digital world.
Modern physics also unlocks power on a terrifyingly massive scale, ironically by looking at the incredibly small. Take nuclear fission. This is the process where a heavy atomic nucleus is violently fragmented into lighter ones. It perfectly demonstrates an extreme scale of physics, splitting microscopic atoms to release immense, city-powering amounts of energy.
But hey, modern physics isn't just theories and power plants. It literally saves lives. Consider why CT scans are so incredibly effective compared to standard X-rays. By taking multiple angular projections and reconstructing them into clean cross-sectional slices, CT scans completely remove the overlap of tissues. It takes theoretical medical imaging physics and turns it into a vital, everyday reality that detects hidden abnormalities in the human body.
Section 5. The final equation. So, what does this all mean? We've covered a ridiculous amount of ground today, from unicycles and ramps to boiling water and splitting atoms. But I want to leave you with this final provocative thought. Physics isn't just about what happens here on Earth. How does physics explain the motions, the energy transformations, and the interactions of the entire cosmos? Well, the exact same rules you just learned, the forces on a ramp, the waves of light, the behavior of atoms, those are the very equations governing the infinite universe around us. Pretty mind-blowing, right? Thanks for joining me on this explainer, and definitely keep questioning the universe.